Good morning, AP Physics. Today will be the last of my 2 videos for review for your test, which is next Thursday, May 14th. These videos will always say that, even though after next Thursday they'll all be outdated. That's fine. So just make sure that you are paying attention to everything. I post a video that gives you all the information you need for the test, so make sure that you have that pulled up. I will be posting another video that's going to say exactly the thing I'm going to say here, but in its own little self-contained version so that anybody else can see that, which is both next Wednesday and next Thursday I am going to be opening up my office hours in my meeting, my Google meeting, to just AP students, just to kind of talk about the test. If you just kind of want to get together to talk to me, maybe you're nervous, or you just kind of want to talk in general, or you want to ask questions about the test, or if there's just things you maybe want to go over, you just want to feel better about it. Again, I'm trying to get a word out to as many people as possible. Hey, Wednesday and Thursday of next week, either day if you want to pop in. I'm trying to get as many people in that meeting as possible, again, in this case, so that we can kind of get a little bit of interaction and be a little bit less nervous about everything. Sorry, you probably can hear my daughter. She's in the background of everything I do, so I apologize about that. She's 2, so that's just how it's going to be. Yeah, so just make sure that you are getting ready for the test, and I am going to cover in this video momentum, and in the next video I will cover energy. There'll be probably a lot shorter videos than the previous video because they're just easier subjects in general to cover. You probably remember that. They were just quicker. They were fundamentally easier subjects to cover. So let's cover, again, in this video we're going to cover momentum, and we're also going to cover in the next video, again, energy. So yeah, I'm probably going to do that thing where I speed up really quickly here because I'm going to take a minute to write down some stuff that we're going to need to talk about momentum. Yeah. So I do that every time, and that's more for me. You probably are like, why is he always doing that? It's for me to know in the video, like, hey, when did I fast forward through everything? So it's way less for you than it is for me. Okay, so let's start from the top. Momentum. So you don't need to know this, but just as this quick background, remember that René Descartes is really the main idea driving behind momentum. Yes, Isaac Newton stated his second law of motion in terms of momentum, but the main thing is that René Descartes was like, hey, there must be some conserved quantity for everything in the universe. For all defined things, there should be some conserved quantity, because he just kind of believed in that balance or conservation of the universe. So that's kind of where we start off with momentum. So, momentum. Really easy. We have 2 or 3 equations in this chapter, and they're pretty straightforward, right? So we have momentum, which is P is equal to mv. That should be pretty easily identifiable and locatable on your formula sheet. There are, again, going to be 3 formulas for this section, although I would imagine that the third formula that I'm going to talk about will not be on there, since it's more of a concept and less of a formula. So we have this P is equal to mv, which P is my momentum, is equal to mass times velocity. Again, you don't need to know this. Remember, P is for pater, or to drive forward. That is because momentum is this quantity that is there when you are moving forward. It is what keeps you moving forward, if you want to put it that way. As long as you still have momentum in a direction, you will be moving in that direction, right? So again, you can see that. That idea is pretty clear. If you are an object, you have mass, right? You actually occupy space, and you are moving, then you must have some momentum. So that's the idea here, right? Again, that is a quality completely dependent on am I moving or not. So if I am moving, it doesn't matter which direction, I have momentum. Momentum is a vector number because of that, though, right? Because momentum, we can get negative momentum, and that just tells me I'm going in the opposite direction that I defined as positive. So just make sure we recognize that, right? You can have negative, 0, and positive momentum. It just says, are you moving? So if an object is moving, it has momentum. And that's almost the main idea for the entire chapter here, other than the idea, obviously, of conservation. But remember that. We're tracking moving objects when it comes to momentum. Now, these are all relative momentums, or relative motion, if we want to put it that way. In other words, I'm sitting still here in my desk, in my chair, so I don't have any momentum. However, the Earth is spinning and going through space. So relative to the ground, I have no momentum, right? Relative to the ground that I'm literally standing on. But, compared to something like the sun or like a comet or something, I would have some very noticeable momentum because I have all of this motion relative to it. So just make sure we remember that as well. Cool. So again, what is momentum? Well, it is P equals mv, but that's just a formula. But you can define it as the conserved quantity of motion. Remember we talked about that inside the chapter. They did an experiment where they moved things around, and they said, well, what stays the same before and after this thing interacts with something, right? Remember, that's what we're tracking in this chapter is interactions, is a force being applied. Remember, that's how we define forces, is that they are interactions between objects. Like if I touch a wall and it touches me back, that is an interaction pair. We have motion. Again, we did that, okay, that's where we were at. We did this experiment, and it showed that the thing that was the same before and after an interaction, again, is momentum. It wasn't velocity, it wasn't speed, and it wasn't a kinetic energy. It was momentum. And they did all these experiments to check to see if all of those things were true, and when they weren't, they're like, well, there's this other thing that does stay the same before and after an interaction. Okay? So that's what momentum is, this conserved quantity of motion. So that leads us to the unit of momentum, and you can see here the unit of momentum is kilograms times meters per second. And that leads us to the idea that we just talked about. It is a conserved quantity, right? It's a conserved quantity, which means that it stays the same before and afterwards. That PI, my momentum initial, is the same as my momentum final. Now that requires us to define a system. Is it a closed or isolated system? Because again, let's say I have an open system and I throw a ball against the wall and the ball stops. You go, well, that's not the same momentum before and after an interaction. You go, well, right, because that's an open system. Things are leaving it. So remember that the conservation of momentum actually states that in a closed system, that momentum will stay the same, right? So a closed system is one where mass doesn't leave the system. So let's say I get into a car accident and pieces of the car fly off. Well, all of a sudden that is an open system. Unless I go back and account for every single piece that it flies off the car, then I can't say like, well, all my momentum stayed the same. We did simple momentum, ball running into a ball. We don't lose any mass. And when ball runs into a ball, that momentum should be conserved. Now we know that some of it goes into other objects, and that's where it gets difficult, right? So when a ball rolls across the desk, it is going to lose some speed or some momentum into the desk. Now the desk is on some level actually accepting that, right? When the ball goes over the desk, even if it just generates heat, that heat is the motion of the particles, and so there is some motion that is being transmitted to the desk, right? So again, that is this idea. Momentum beforehand has to be the same as my momentum afterwards. And again, that's most of what the chapter is, right? Most of the chapter is they're going to give us an interaction. Ball runs into ball. So I have a stationary ball and I have a ball that moves into it, right? You can't see that. But when the ball moves into this, we're going to have this interaction. So let's say it happens exactly like that. So this ball is moving. It has momentum. This one doesn't. Boom, they hit each other. This is going to be the interaction, and then after the interaction, this one stops and this one keeps moving. So what we know is this ball must have all the momentum of this ball. And you go, why? Well, very easily, because it's a closed system. I only have these two objects, and if one object no longer has momentum and the other one does, it must have all of the momentum of the previous object. And that's almost everything we're doing in this chapter. Everything else is just adding extra items, right? So let's say I have 3 balls in a row. All I have to do is go track the motion of all the balls in a row, right? Let's say that I have 4. You get it. All we're literally doing in this chapter, or in this unit, was pretty much saying is something moving or not. Because if something is not moving, it doesn't have momentum. That's pretty much it. We're really just tracking moving objects. So that's the number one question to ask yourself in any one of these questions is, what's moving? Because if it's moving, it has momentum. Hey, what's stationary? Doesn't have any momentum. And obviously you need to go back and forth in terms of sometimes you're going to have these interactions where something will start to move, but we're talking about, again, before and after an interaction. Now, what is this interaction? Well, this interaction is a thing called an impulse. And an impulse is a force applied over a time that causes this, transfer of momentum. Now, an impulse is usually defined as being outside the system, right? Not usually, that's just what it is. And that means that if two things interact inside the system, they're just objects. This object has momentum and this object has momentum. But if I define my system object, and it gets momentum and it seems to come from nowhere, we know that it actually has to be coming from this thing called an impulse. I accidentally erased something with my hand because I'm dumb. All right. So again, this impulse is this interaction. And so, again, we can see impulse has 2 different symbols here. It's got this J with a vector symbol on it, and that's because impulse is a vector number. Why? Well, because the force applied is a part of it, and direction of force obviously matters. Okay? So we have this impulse, a transfer of momentum from outside the system. Okay? So again, I can literally do this, right? I can literally do this. You can see I have this marker. This marker has, if I can get this, yeah, well, we'll do that. This marker has no momentum. Let's say the marker is the system and I go and do this. Marker moves, I am in the impulse. I applied a force to it over a time interval. Yeah, and that's pretty much it. So if I get a transfer of momentum from something that's outside the system, that's an impulse. And something that's an impulse can take away some of my momentum, or it can add it. It all depends on if it's applied in the direction I'm traveling or the opposite direction. So again, if I'm running and the wind blows against me, the wind is an impulse. It's a force being applied to me over time. And by way of that, it's going to slow me down. So that's going to be an impulse that takes away some of my momentum. Again, the other way would be true. If it blows behind me, the wind makes me speed up, that is a positive impulse. Again, the idea literally just being, does it add or subtract any sort of momentum from the system? And if this impulse doesn't interact with my system, then it's not really an impulse. It's just a force happening somewhere else. It may be an impulse to another system, but not for us. Yeah, so that's pretty much it. Thankfully, this chapter is really straightforward and easy. I am going to do still a quick run through because there's one concept that I didn't get a chance to write out here that we didn't cover, and then I'm going to do really brief examples because they're pretty easy. And I'm not going to spend too much time on momentum, but just make sure you kind of look through this. Same thing with energy. It was pretty straightforward as well. Yeah, so I'm going to do that thing. I'm going to erase all of this. And then I'll come back and we'll talk about this other concept. Okay. So got all this written out. Let's go through it as quickly as possible. So we have this idea called the impulse momentum theorem. Now remember, a theorem is just another way of saying, hey, we have this idea and we put it in formulaic form. So in this case, it just says something we've already talked about, that a impulse, F delta t, is a change of momentum or a transfer of momentum. Now again, this is from outside the system. Inside the system, we're just tracking the momentum of other objects. We'll talk about that here in a second with an example. So that's another way that we can just say, all right, so F delta t, or my impulse, is my final impulse minus my initial impulse, right? And so we can do two things with that to help us solve out for some pieces. So the first one here is I can say, okay, if I find out what my original momentum is and I add in what the change in momentum is, it'll tell me what I end up with. Pretty straightforward, right? It's basically like saying, okay, I had 5 kilograms times meters per second momentum, and then something bumped into me with another 2 units of momentum, and so now I have 7. Pretty straightforward. The other thing that we can do with this is this, and it allows us to solve for what is our average force. So let's say that I know that something is pushing against me for 4 seconds and I experience transfer of momentum. Well, that's going to allow me to go back and figure out what was the average force that is applied to this thing over that amount of time. And that's a good thing because sometimes we'll need that to figure out things like the acceleration of the object or eventually like the velocity, things like that. So sometimes you'll see that where they're trying to get you to relate those concepts. Because remember, force is still related to acceleration. And so in this case, I can use the force after I've calculated it to find the average acceleration and to go back and find some velocity and some distances and things like that. Do I know that they'll do that? No, but that's an easy way for us to go back and do that. Cool. So that brings us to a little example I've got for you. So let's say that I've got this box. I'm going to call it box 1. So let's say that box 1 is traveling across a surface and that it's going, it has a mass, of 4 kilograms and it's traveling 10 meters per second. Right? We don't care about if it's slowing down or speeding up. Don't worry about that. So let's say that we're going to have a question on the test that gives us this idea. It just tells us, hey, we have a second box, right? And it has the same momentum as the first one. So the momentum of box 1 is equal to the momentum of box 2. And so that allows us to do the following. Let's say that box 2 has a mass of 2 kilograms. Okay, so that allows me to actually go back and figure out how fast is box 2 traveling. Because I can say, okay, the momentum, or the mass times the velocity, right? You can see that we have the mass times the velocity. The momentum of object 1 is literally going to be the same as the momentum of object 2. The thing that'll change is that box 2 will be going faster because it's lighter, right? So again, if we have an end result that's the same, but we change one of the factors, then the other one has to change to accommodate that, right? So we can see here, again, we have that mass times velocity of the first box times the mass times velocity of the second box. And so that allows us to go back and solve here pretty easily, right? We have this 4 times 10 over 2, right? That's just me dividing the kilograms out. Gives me the 20 meters per second, which is going to be here the velocity of my second box. Really easy, right? Again, this section was actually straightforward. Yes, you can do it in 2 dimensions. It's the exact same idea with everything else we did in 2 dimensions. Sine and cosine, split them out, come back later and put them together. And if you need to put the x and y together, Pythagorean theorem. Again, sine and cosine and all of that stuff, I didn't cover a lot because it's trig, it's pretty recursive, and I hope that you recognize it, but if you don't, make sure that you do recover trig. They have all the trig stuff on the formula for you. Just make sure you do cover that. Okay. So this is my last example for momentum, and we are almost done because it's just not that much in this chapter. Not that there's not that much, but you can demonstrate all of it in relatively short, easy to track examples. Because remember, it's momentum. It's only moving objects. We only care about objects that are actually actively moving. Okay. So let's say we have this scenario. Let's say we have two balls that are rolling, and they are both rolling, right? One of them is rolling faster than the other one. It's going to run into it, right? So we can see this ball is going 4 meters per second is going to run into this ball, but we don't know how fast it's going. And then afterwards, the first ball is actually going to stop. And the second ball will keep moving, and we know that it's going to keep moving at 7 meters per second. So it's going to, we assume, speed up, right? Because obviously, if it was going faster than the first ball would never run into it, right? So we assume that it's going to speed up, but we don't know. Both balls have the same mass. Cool. So let's say that those two balls are the only things in our system. Because those two balls are the only things in our system, this will hold true, that we have momentum the same as the momentum afterwards. The next thing we're going to do is say, how many things are moving before and after this interaction? Because each one of those things is going to have their own momentum. Well, here we have two objects moving before they interact, and one object moving after they interact. So we're literally just going to pump in an equation of momentum for every one of those moving objects. Object 1 gets its before momentum, Object 2 gets its before momentum, and Object 2 gets its after momentum, since it's the only one moving. Cool. So that means that we could just plug those numbers in, right? And we go, okay, so 2 times 4, which is the momentum of the first object beforehand, plus 2 times velocity, which we don't know what it is yet, we're going to solve for it, is equal to the final velocity. Remember that when we're doing this, we are literally just adding up all the individual momentums of every object, right? We are literally just adding them up, almost like we did with the sum of all of our forces, right? We just went and identified all of our forces and added them together. In this case, we are literally just identifying what objects are moving, add their momentums together. So now that I have this, you can see I have one unknown. That velocity, that v in that second term, is the only thing I don't know. So if I plug in everything else, I'll get 8 plus 2 times v is equal to 14. So if I subtract the 8 from the side, it'll give me 2 times v is equal to 6, which will give me velocity is equal to 3 meters per second. And that's not even the easiest way to cover that. And there's multiple ways that you can go through and do that, right? What you could literally do is not plug that stuff in, move your terms to the other side, kind of pull them out, and then go, oh, all I had to literally do is add those 2 meters per second together, right? All I had to do, or I guess that's kind of me screwing it up. All I had to do was subtract the 4 from the 7. Because the two objects have the same mass. Not everything's going to be that way, but in this case, because the objects have the same mass, it was pretty easy for me to go, oh, okay. So if it gets all of this momentum and its mass is the same, the only thing that's going to change is it's going to gain all of that meters per second. Pretty straightforward. So again, there's a couple different ways to do that. That is a couple different examples for you. Momentum is really straightforward and easy. So I hope that didn't take too long for you, and I'm going to cover energy in my next video. I'm going to get that done today as well. Again, they're both pretty straightforward. You just let me know if you need something else. I probably in the next video will write it all out before I even do the video. That way you won't have to see all these little like skip sections, unless you like the little skip sections, which hopefully you don't. So I appreciate that. I'll get this posted. It'll be the last review video, so just make sure that you are doing as much as you can there, and I appreciate you checking in with me.